So all the grade 11s during block E on Thursday go to confession. Yeah, so not going to affect this block, but just a heads up because it will affect you folks. Let's start with a quick prayer. In the Father, Son, and Holy Spirit, amen. Who are bless the rest of the people, bless our down on women, bless for the God of Jesus. Holy Mary, of God, pray for us sinners now and at the hour of our death. St. Thomas More, pray for us. Nice. In Jesus' name. So when you hear your name called, if your phone isn't yet where it should be, please place it there. Julia, Daniel, the other Daniel, here. Olivia, here. Samantha, Julian, here. Claire, Allison, Lauren, Randall, here. Samantha, Brianne, Nicole, Sandra, Annika, Christina, Beckus, Alexandria, Annabelle, Mayan, Ariana, Leah. So today, I want to finish 5.3, and upon finishing 5.3, I want to show you the first of two videos. The first video that I'm going to show you is for the end of 5.3, the second is in 5.4. So what I'm going to show you today is, it was off a series in PBS years ago called The Mechanical Universe, which chronicled the major discoveries in science throughout the 20th century. So there's a whole bunch in the video, but the chunk of it that I'm going to focus on is the part on quantum mechanics. There are a couple of things in there that I disagree with. I think one of the professors, in his attempt to make it simple, doesn't actually correctly express what we believe quantum mechanics means about electrons. And one of the things you'll notice in the video when we get to it is that they never mention Louis de Broglie. They mention Schrodinger, but they don't mention de Broglie, and they certainly don't reference the fact that he got the Nobel Prize for suggesting that particles have a wave nature. And the physicist that I'm talking about says, in other words, an electron is a point particle. That's not one of the foundational opinions of quantum mechanics. To some extent it's semantics, but there's a whole bunch about electron behavior you can't explain if you see it as a pure particle. And I think that's why they choose to ignore de Broglie's name. You'll see a picture of him. I'll point out which of the guys in this photograph is de Broglie. It's just, I think they do a disservice for not mentioning his name at all. Maybe because it was for television and not for scientists, and maybe they thought that was just a little too weird for people. But at any rate, I will sort of pause the video or at least comment on it as we're going through it, okay? So we ended off last class introducing de Broglie's equation. You don't have to memorize the equation, but if you see it, you should be able to say something about its significance. So, for example, if you look in the bottom of page 262, there's the equation. And what it tells us is that the mass of any particle is inversely related to its wavelength. And they're related through a very tiny constant. The only time you need to concern yourselves with the wavelength of a particle is if that particle is really small. And remember, the only thing I wanted you to remember about Planck's constant is that it was exactly that, really small. And we're going to see another equation, another inverse equation today using Planck's constant, and the same thing applies. Okay? In other words, you only have to worry about this when you're talking about things that are really tiny. So let's go to Heisenberg, Schrodinger, and orbitals, okay? And that's gonna finish 5.3. 5.3 is really the theory part of it. And at the end of 5.3, even if most of what's in 5.3 is difficult to wrap your head around, don't worry about it, you're in good company. But the fact is, it works. And there's another, my favorite guy in the video is a physicist from MIT. He looks homeless. He might not even know that MIT has a dental plan. But he's just a pure scientist. And you can tell that he's enthusiastic about what he's doing. But near the end of the video, he said, people ask me if I understand it. I don't know what the meaning of that word understanding is. And then he says, as long as physics, as long as the formalism applied in the right circumstances gives the right answer, who cares what understanding means? So I like that because he's not arrogant, but he also admits, I don't really understand it, but who cares, it works. That attitude is what we're going to bring into section 5.4. In other words, even if you have trouble making sense out of this, the fact is it works, and we're going to use it to describe electrons and atoms. We're going to use quantum mechanics really to populate all of the electrons in all of the elements in the periodic table. Okay? So, there's only a couple pages yet to go, but they take a little more time. As mentioned earlier, not everyone was comfortable with the idea that electrons could be both a particle and a wave. And two of those scientists that had sort of opposite ideas about electrons was a young German physicist named Werner Heisenberg and an Austrian physicist named Erwin Schrodinger. Heisenberg treated the electron as a pure particle, and he kind of invented a branch of mathematics all by himself called matrix mechanics that he used to describe electron behavior. Around 1925, two competing mathematical theories existed that attempted to explain and predict electron behavior. As it turned out, neither was sufficient, but they were both coming at the same problem from different directions. Werner Heisenberg, a young German physicist, developed matrix mechanics, which involved complicated and difficult equations that physicists hadn't seen before. And they weren't comfortable working with the form of math that they weren't familiar with. It treated the electron as a pure particle with quantum behavior. It ignored any suggestion that it could behave like a wave. An Austrian physicist named Erwin Schrodinger did the exact opposite. He rejected the idea of an electron as a particle. He said, okay, according to de Broglie, it can behave like a wave, so let's treat it 100% like a wave. He decided to treat the electron mathematically as a pure wave. And physicists were a lot more comfortable with wave equations. In his wave mechanical description of the electron, Schrodinger used an equation to describe the electron as a wave function. The math was easier than the matrix approach, or maybe more familiar. And the wave equation was popular with many physicists. But the video kind of suggests that Erwin thought about the wave nature of an electron on his own. He didn't. He was only doing this because de Broglie had suggested it could have a wave nature. Okay? And remember, once it was shown that an electron did have a wave nature, de Broglie got the Nobel Prize. Each of the two scientists believes that his interpretation was correct, yet neither seemed able to sufficiently predict the mysterious comings and goings of electrons. Within a year, actually a colleague of Schrodinger named Max Born, about a year after the wave equation was proposed, Born basically said, this is what this thing is really telling us. I don't think Schrodinger even understood it himself initially. Within a year, it became clear that matrix and wave mechanics were actually different ways of getting to the same answers. Soon, Heisenberg and Schrodinger became crucial contributors as quantum mechanics was eventually united into one theory. Now, this is something else that the video gets wrong. The the physicist with whom I take a little bit of exception, kind of has the history incorrect. He said that one day Heisenberg was so worried about how to describe the electron that he came down with a bad case of hives and hay fever. Stress doesn't cause allergies, okay? The fact is, Heisenberg was teaching at the University of Göttingen, and he did have a hay fever attack. He suffered from allergies. And so he decided to take a break, take a leave of absence. And he went to an isolated island in the North Sea where whatever was causing his allergies were no longer there. He isolated himself. Then he began to think about ways of describing the electron. During his stay, he focused on the problem of electron measurement. After much thought, he came up with one of the most important principles of modern physics. Heisenberg identified a fundamental uncertainty associated with measuring any particles. He called it the uncertainty principle. In the form of a simple equation, the principle stated not that it was difficult to know exactly where any particle was and where it was going simultaneously, but impossible. Furthermore, the more certain you became of one measurement, like where something is, the less certain you were of the other, where it's going, and vice versa. Much like de Broglie's hypothesis, the equation for the Heisenberg uncertainty principle appeared quite straightforward, but the ramifications were enormous. The principle can be written this way. Now, you guys know pi, that's a constant, and you know Planck's constant, which is another constant. So obviously that is a constant. So this tells us that two things multiplied together are greater than or equal to a constant, which means these two values are inversely related. M is mass. Delta V, think of delta as uncertainty, plus or minus, range, okay? And V is velocity. And you guys know that velocity is a vector quantity. So delta V is the uncertainty in where something's going, okay? Delta X is the uncertainty in its position. So let's say that that's delta X, okay? Whatever we're looking for is somewhere in here, that type of thing. And I explain it on the next page. M is the mass of a particle. Delta V equals the uncertainty in velocity, where it is, in other words, where it's going. Delta X, the uncertainty in the position. H is Planck's constant, and you know pi. Think of the symbol delta as representing the plus or minus value, spread of results, uncertainty. The equation shows that the uncertainty in where a particle of constant mass is going, how fast and in what direction, multiplied by the uncertainty in where it is, delta X, is greater than or equal to a very tiny constant. This means that the two values are inversely related, which is to say, as one goes up, the other goes down. The equation tells us that as we become more certain about an object's position, delta X decreases. Okay? And that's just in 2 dimensions, like imagine 3 dimensions. The uncertainty in where an object's going increases, and vice versa. The more we're sure about where something's going, the less sure we are about where it is. And the more certain we are about its position, the less we know about where it's going. Now that seems weird. This certainly isn't our experience in the world of objects. For objects big enough to see, such as cars and baseballs, it's easy at any point in time to say both where they are and where they're going. And if it wasn't, then the world of big moving objects would be a very dangerous place to live. So imagine you're stepping off a street corner at an intersection and you're crossing a crosswalk. And you know there's a bus coming towards you. You know where it's going, but you don't know where it is. Or you know where it is. It's really close to you, but you don't know where it's going. It could either be going that way or this way. Dangerous place to live. That seems absurd. Once again, a similarity to de Broglie becomes evident, as again we see an inverse relationship involving Planck's constant. And once again, the fact that that constant is so small means that the uncertainty principle only matters on the atomic scale. Just like de Broglie's wave equation only matters at the atomic scale. And remember, the only thing I wanted you to remember about Planck's constant was that it was really tiny. The key to understanding this principle at the atomic level is to ask ourselves how we see anything. So how do you guys know I'm here? Let's say I wasn't talking. How do you know I'm here? Nobody knows? That's an interesting question. If the room was pitch black, would you know I was here if I wasn't talking? So we turn the lights on, and now you know I'm here. So what happened when you turn the lights on?
We can see you.
Sorry?
We can see you.
Exactly, but how? In other words, how do you know I'm here?
Because of the light.
Keep going.
It's like bouncing off you.
What's bouncing off me? Remember, light can be a particle. So what's bouncing off me?
Photons.
Starts with a pH.
Photons.
Photons. Yeah. That's the only way we see anything.
I'm using photons to see you right now.
Suppose, for example, that we were given a flashlight and told to locate a baseball thrown into a dark room. No problem. We simply turn on the flashlight and we immediately know where the ball is and where it's going at the same time. You go, duh, of course. Of course, the countless photons striking the baseball have no measurable effect on it because of the ball's large mass. But what if we used an atomic bomb to supply the energy to illuminate the baseball? Obviously, that amount of energy would blow the ball and the room and the building probably half of the neighborhood away, so that nothing meaningful concerning the ball's position or motion could be known. So that sounds silly. Seeing an electron also requires that some form of illuminating radiation bounce off the electron. And there lies the problem. Because the mass of an electron is so unimaginably small, 9.11 times 10 to the minus 31 kilonewtons. Even the energy of one photon striking the electron is more than enough to blow it away in much the same way that the bomb would blow away the baseball. Stated another way, for quantum systems, which means really small, the very act of measuring something causes a significant change in what we're measuring. We can't find it unless we change it, okay? This applies to any measuring method we know. So if Heisenberg was right, then finding an electron where it is and predicting its behavior where it's going isn't only difficult, it's impossible. So let's elaborate on that for a second. Let's say this room is pitch black. And let's say that I'm told somewhere in this room there's a balloon. And it's floating somewhere in this room. And I'm supposed to find it with this meter stick. Now, is it gonna do me much good if I do this? Because as soon as I find the balloon, any chance it's still where it was when I smacked it? No, that's stupid. So what if I just tap it? Well, let's say I hold a meter stick like this, pitch black, I'm walking around the room, and I just tap the balloon. Now, if I just tap it, I haven't moved it much, right? So I haven't affected where it's going. But if I hit it like this, then I don't really know where it is. It's somewhere in this length, right? Okay. All right? Obviously, if I could shrink this distance, in other words, if I could turn this into that, now what if I tap the balloon with that? That'd be good, because I didn't move it much, and now I'm pretty sure of where it was at the same time. Problem is, you can't do that. What am I looking for an electron with? A photon. I'm trying to find it. Photon is a packet of light energy. Didn't I put this equation on the board before? Frequency and wavelength are inversely related to the speed of light, right? And remember this. There's Planck's equation. Okay, let's say what I'm looking for the electron with is a photon, a wave packet, if you will. And let's say the wavelength of the photon I'm looking for the electron with, let's say it's that. Okay? That bounces off the electron. This bounces off the electron. If that thing comes back after hitting an electron, I kind of know where it was, but not really well, right? Delta X is too big. So then you say, well, dumbass, shrink the wavelength. Okay. What if I hit the electron with a photon, say with this wavelength? Now, if that bounces back, delta X is a lot smaller, right? Which is good. In other words, that would be analogous to taking the meter stick and going from here to here. So tap it with that. I can't. What's the only way to reduce wavelength? What happens when that goes down? That goes up. What happens if frequency goes up? Energy goes up. So in other words, I can tap it with this, but I can't tap it with that. If I want to shrink the wavelength, that's doing that. There's no compromise. I can't get a low energy, short wavelength photon. Impossible. It's either short wavelength, high energy, or long wavelength, low energy. Long wavelength means I don't move it much, but I don't know where it was. Short wavelength means I know where it used to be, but I smacked it so hard it's no longer there. They're inversely related. Okay? Which is kind of disturbing, because the volume of any atom, which makes up all matter, is defined by an electron cloud. And if I can't say with certainty where an electron is and where it's going simultaneously, what I'm forced to accept is matter at its most basic level is indeterminate. I can't say with certainty anything about matter. The obvious question is, how can we then describe atoms at all? Electrons and atoms at all? The answer comes in the form of a compromise from Schrodinger's wave equation. The equation is complicated, and we needn't worry about solving it here. It's full of partial derivatives. It's calculus, and it's a complicated equation, but we can kind of get an idea of what it tells us relatively simply. What it tells us about electrons is important. Schrodinger represented the electron as a wave function, and he used the Greek letter psi, which kind of looks like a pitchfork. Okay? The wave function is obtained by solving Schrodinger's wave equation using the allowed energy states associated with electrons and atoms. So, what do we mean by that? Well, Schrodinger used the allowed energy states in the Bohr atom, which seemed to have credibility because of its success in describing the hydrogen atom. So, you guys are familiar with sort of a two-dimensional Cartesian plane, right? X and Y. Let's imagine that that's the nucleus. But we need a three-dimensional arrangement. So let's say we have a third axis, maybe coming out of the board. Okay? And you can call this X, because that's probably what you're most familiar with, Y, and Z. Doesn't matter what we call X, Y, and Z. The point is, they're all at right angles to each other. So there's the nucleus. So what Schrodinger's equation does is it gives the electrons we're trying to describe energy equivalent to the allowed energy states in Bohr's atom. In other words, because of that nucleus and the negative charge in the electron, let's give an electron energy associated with n equals 1. And for that energy, what the equation really does, it tells us where the intensity of the electron wave is the greatest, where the amplitude of the electron wave is the greatest. And what that really tells us is where the electron most probably is. So the regions in 3D space around the nucleus, where an electron with a particular energy has the strongest wave, that's a place where we're likely to find it. And if we enclose all those regions of high probability, where the wave amplitude for the electron is the greatest, wave amplitude equates to probability of finding it. If it's most intense there, that means it's probably going to be there. And we enclose those positions of high probability in a shape, and we call that an atomic orbital. The regions in which there is the highest probability of finding electrons with those amounts of energy are called atomic orbitals. So there's the definition. Atomic orbitals represent those regions in three-dimensional space around a nucleus. They're not a path, they're a region in space around a nucleus where electrons with a particular energy are most likely to be found. Not are found, because we can't say that. Are most likely found. So probability, as the video suggests, is woven into the very fabric of matter. Einstein couldn't live with that. Einstein, there's a historian from Harvard who describes Einstein's view of physics in a certain way. One of Einstein's most famous statements is, God does not throw dice. He did not believe that the universe was governed by the laws of probability. And as I think I've said before, some of the most famous, if not the most famous scientific debates ever were between Einstein and Bohr. And whenever Einstein would say God does not throw dice, then Bohr would say, nor is it our job to prescribe to God how we should run the world. So, as the historian from Harvard said, Einstein believed in a universe of complete law and order, where a set of equations, deterministic, causal, would be able to predict an event in the future precisely given the parameters of the present. Quantum mechanics says that that's not happening, okay? Think of an orbital as a probability volume or a charge cloud, not a path, representing a three-dimensional picture of where we will probably encounter electrons around the atom's nucleus. For different allowed energy states, different numbers and types of orbitals exist, and we're going to discuss all of those in section 5.4. Section 5.4 is where we apply everything that we eventually arrived at up to the end of 5.3, okay? So it seems that probability is woven into the fabric of matter at its most basic level, and many scientists, most notably Albert Einstein, resisted this idea. One of Einstein's most famous statements regarding his objection to the uncertainty principle was, God does not throw dice. Note the difference between Bohr's electron orbit, which is a path specified by a moving particle. As convenient as it is to see the Bohr model as a little planetary system, there's never been any evidence that electrons follow a path at all. And the Bohr model has effectively been abandoned. Okay? No evidence exists that electrons follow a particular path. Rather, quantum mechanics views electron behavior using the mathematics of waves to determine the probability of finding that little particle wave around the nucleus. This is an orbital. That's all we can do. Werner Heisenberg was awarded the Nobel Prize in 1932, and Erwin Schrödinger received the honor the following year for their contributions to quantum mechanics. Now, it's almost semantics. Does that mean that an electron is a particle, and Schrödinger's wave equation tells us the probability of finding it? You could, if that works for you, that's fine. Or you could say, well, the electron's a particle wave, and wherever its amplitude is the greatest around the nucleus, that's where that thing is most likely located. But if you ignore the fact that it has a wave nature, you can't explain quantized energy levels. Because unless you incorporate the idea of standing waves, And there is no explanation for the quantized energies associated with electrons and atoms. And there's three important aspects of the quantum mechanical view of the atom. Number one is exactly that. The energies of electrons and atoms are quantized. That's courtesy of Niels Bohr. But he didn't know why. The why came courtesy of Louis de Broglie. This relates to the idea that only certain allowed energy states associated with standing electron waves can exist. And if you don't accept the fact that the electron is also a wave, you can't explain quantized energy. Number two is the Heisenberg uncertainty principle. Remember, both of them contribute. Heisenberg's uncertainty principle that says that it's impossible to simultaneously state both where an electron is and where it's going. Don't just say where a particle is, because things big enough to see, we can say where they are and where they're going simultaneously. Were we not able to do that, we wouldn't be alive. But with an electron, you can't do that. And then number three is the compromise, courtesy of Erwin Schrödinger. So, Bohr, Broglie, Heisenberg, Schrödinger. Atomic orbitals are those regions in three-dimensional space around a nucleus where electrons with a particular energy are most likely found. So there's really four aspects to it. Regions in 3D space, not paths. Where? Around the nucleus. Where electrons with a particular energy are most likely to found. If you leave out the most likely and say are found, it's wrong. That's the whole point. Okay? That's a promise as a test question. Okay? The test on chapter 5, and we definitely have that as a written response question. Now, as I said, you might go, how can that possibly, that doesn't make any sense. Well, if it doesn't, if you don't understand it, as you're going to see on the video, you're in good company. If you look at the activity, I couldn't figure a name, so I just came to me on a bike ride. Uncle Werner says, consider this. Why must the Heisenberg uncertainty principle be considered when discussing quantum systems? Which again is science speak for really small. Consider the following two scenarios and answer the questions below each one. Student A and student B are each given identical lab thermometers. They're asked to measure the temperature of the water in a large heated swimming pool as accurately as possible. The water temperature is about 35 degrees Celsius. Each thermometer reads room temperature 25 degrees Celsius. Student A lowers her thermometer bulb into the water in the pool. She waits for the reading to stabilize and then records the temperature. Student B places 5 milliliters of pool water into an insulated test tube and then places the thermometer in the test tube and waits for the reading to stabilize and then records the temperature. Which reading will more accurately reflect the water temperature of the pool and why? So this is effectively an analogy reflecting Heisenberg's uncertainty principle. Ask yourself this. Any chance that the 25-degree thermometer is going to change the temperature of a pool full of water? Remember, the thermometer's 10 degrees colder than the pool water. Any chance that the pool water is going to cool down when the thermometer goes in there? No. The thermometer's the photon, and the pool is me. Any chance photons bouncing off the mirror are going to bounce me around the room? No. It's any chance that a 25-degree thermometer immersed in 5 milliliters of pool water is not going to change that temperature? No. In other words, the thermometer is going to unavoidably interact with what it's measuring because the sample is too tiny. 35-degree pool water is going to instantly cool down when a 25-degree thermometer goes into 5 milliliters of pool water. That's the quantum system, the 5 milliliters of pool water. We'll take it to its extreme. A drop of pool water. Touch the thermometer bulb to that drop. Any chance that drop is going to stay at 35? No. Any chance that the electron I'm looking for is going to be struck by a photon and not go all over the room? No. Or scenario 2. Student A and student B are each blindfolded, given a hockey stick. I thought I'd use a hockey stick because I'm Canadian, and placed in identical airplane hangars. Somewhere in the hangar where student A is standing is a school bus. Somewhere in the hangar where student B is standing is a small balloon floating light up. The students are told to find the object in their hangar by swinging their hockey stick as fast as they can until they hit the object. As soon as they find it, they must stop at the place where they encounter that object. Which student's final position will more accurately reflect the final location of the object they're looking for and why? Well, consider student A. Any chance that when that student hits the school bus with the hockey stick, the school bus is going anywhere? No. The hockey stick's going to have no effect on the school bus. Just like a photon's going to have no effect on me. Any chance that when student B swings their hockey stick and hits the balloon, that the balloon is still going to be there? No. The balloon is the electron. That clever pair of analogies kind of is a way of analogizing Heisenberg's uncertainty principle. Some of the review questions are worthy of note. What do the two theories of Max Planck and Louis de Broglie taken together mean about the existence of pure particles and pure waves? Well, Max Planck said that waves can behave like particles. Louis de Broglie said that particles can behave like waves. So maybe it means that particles and waves at some level are the same thing. It suggests particle-wave duality. There is no such thing as pure waves, and there is no such thing as pure particles. Look at number 8, maybe. Suggest a reason why we can ignore Heisenberg's uncertainty principle when locating macroscopic objects such as cars and baseballs. Again, this relates to Heisenberg's uncertainty, or the Planck's constant. The only reason we need to concern ourselves with the uncertainty principle is for objects that are really, really small. And if they're small enough, then the act of looking for them unavoidably changes them significantly. And there's other ways to look at that, like it's almost semantic. One of the things that the narrator in the video says at the outset is, in quantum mechanics, things don't exist until we look for them. Well, it's almost by looking for something we cause an event. We cause something to be. And there's a clever little thought experiment called Schrodinger's cat. You can Google it if you want. But it's kind of the idea. We don't know what something is, this way or this way, until we look for it. And the idea, it's in a nutshell, Schrodinger's cat is a cat in a sealed box into which there's a sample of a radioactive material. And that sample is going to emit radiation that kills the cat. But we can never predict when that emission will occur. So, until we open the box, the cat is both alive and dead. We don't know if the cat's alive, we don't know if it's dead, until we open the box. In other words, until we look at it, until we do that, both things exist. That's kind of the idea with the electron. We don't know what it's doing until we look for it. And by looking for it, we cause it. Yeah. Yeah. Number 10 is a reasonable test question too. Maybe not exactly those guys. But remember I said I don't care about years. I just care about what. So if you had to write one written sentence explaining what each of these people did or contributed to our understanding of atomic structure, could you? Now, the answers are in the book. You can light this up and find it. But this isn't memorized stuff. This is, could you put it in your own words? That might be a test question too. I've been almost regularly surprised / disappointed at how difficult it is for students to write one well-written sentence. Some students think as long as they keep putting commas in there, it's a sentence. Nah, it doesn't work that way. And I think writing is becoming an increasingly lost art. But now section 5.4 is applying it. We're not going to do that today. That's coming up. I want to show you the video. It's a portion of the Mechanical Universe. I ordered this from PBS several years ago, and it wasn't made for a science class per se. It was a television program. So maybe that's why they leave it totally out. I'll turn the lights off in a second.
This time, it's too weird for Einstein himself to accept.
So the one that just came before this is relativity. So relativity is just ended.
The awards committee to accept. Instead, Einstein is honored for other contributions. Quantum mechanics. Quantum mechanics comes out of the struggle to understand the structure of atoms. What physicists in the early 20th century learned is that in the world of the very small, the seemingly impossible is commonplace. Things don't exist until someone looks at them. We're unable to say exactly what path something takes to get from point A to point B. Uncertainty and chance are woven into the very fabric of existence. One of the key figures in the quantum revolution is a young Dane with a tendency to mumble. He's the scientist on the right. His name is Niels Bohr. And from childhood, it's physics that consumes him. Once, while playing goalie in an important soccer game, he starts scribbling equations on a goalpost. It screams of an ardent fan, snap him out of his reverie in time to stop an opposing player's potential goal. At school, he's an excellent student, though he seems to have a serious phobia about writing. As a graduate student, he dictates his entire doctoral dissertation to his mother, causing a family fight when his father insists that their budding PhD learn to write for himself. He never does. After his marriage, his wife gets the job. In 1912, shortly after receiving his doctorate, Bohr travels to England. He comes to Ernest Rutherford's laboratory just 1 year after Rutherford makes a startling discovery about atoms. Atoms had been seen as amorphous blobs of positive charge studded throughout with negative electrons. In fact, Rutherford says, they're more like little planetary systems. All the positive charge and virtually all the mass is concentrated in a tiny nucleus, around which the electrons orbit like planets around the sun. This is the courtyard at Cambridge University, where Rutherford began and ended his scientific career. Imagine an atom this size.
If we think of that being the size of an atom, then the size of the nucleus will only be 1 millimeter in diameter. That's a bit smaller than this little grain of sand that I've got in my hand here. In other words, what it means is atoms are essentially empty space.
Now, how can we reconcile that with the fact that matter is matter, and my hands don't go through one another? Well, that's crazy because if it's mostly empty space, they should pass right through one another. But what we understand now is, in fact, the reason my hands don't go through one another is that while the space is empty, what it's filled with is really electric fields. When the electrons come within a very small distance of each other, they begin to repel each other. So we have the illusion that things are solid, when actually we have this tremendous vacuum given by the fact that the atom is basically empty. Now this means that I'm not really sitting in this chair at all. The atoms of my body are about 1 angstrom hovering over the atoms of this chair.
Rutherford's conception of the atom is a breakthrough, but almost immediately he finds a paradox at the heart of it.
See, the problem was that if you've got a nucleus with a positive charge and electrons in orbit about it, then we know that the electron should very rapidly orbit into the nucleus. It should do it in a fraction of a second. That's a very secure prediction of classical physics. And that's catastrophic. What it's telling you is that atoms can't exist. It means that you and I would not exist. The atoms would have no way of supporting themselves with the large volumes that they have.
When Niels Bohr arrives in Manchester, Rutherford is ready to abandon his model of the atom. But Bohr sees a way to save it.
He was so excited, he canceled his honeymoon. He had to delay his wedding, cancel the honeymoon, and his poor fiancée, instead of going on a luxurious honeymoon, had to take dictation as her husband dictated one of the greatest masterpieces in physics because he himself could not get himself to write down the paper.
What he proposed was that you would not allow the electrons to move in any orbit about the nucleus, as you could according to classical theory, but only to occupy certain very well-defined orbits about the nucleus. There would be an orbit here, an orbit here, an orbit here, but there would not exist orbits between these.
There's nothing in between. In between exists nothing. And that's very non-Newtonian. If you take the Earth and you could move the Earth a little bit closer to the Sun, no problem. We'd have a different orbit, would be stable, we'd have a different time to go around the Sun, no problem. That you cannot do with an electron around a nucleus. You cannot just change the orbit by a little bit. You have to change it by, so to speak, a lot.
They never explain why.
Bohr's idea that electrons can have only certain orbits draws inspiration from other new theories that suggest heat and light come in units that can't be divided, called quanta. But applying this quantum idea to matter is practically sacrilegious. In fact, most physicists disapprove of Bohr's theory. Whenever they meet, they scoff at the idea that an electron can be in some places but not others, that matter comes in some sizes but not others.
If it's not nonsense, at least it doesn't make sense.
And this is just a cheap excuse for not knowing what's going on.
The assumptions are too bold, too fantastic. They can't be right.
In time, two camps emerge. A group around Bohr, which believes in his so-called quantum theory of matter, and those who cling to the classical view. No less than the true picture of nature is at stake. In 1926, Werner Heisenberg, a 25-year-old German physicist, comes up with a mathematical description of atoms that goes a long way toward legitimizing Bohr's view. Classical physicists remain unconvinced. Heisenberg's mathematical matrices are too complex, and the mysterious comings and goings of electrons are just too hard to imagine. Within a year, an Austrian named Erwin Schrödinger offers an alternative.
Schrödinger had this beautiful theory of the electron as a wave. It was smeared out over space and time. It wasn't a particle at all. Physicists loved this idea. We had a physical picture. We could look inside the atom. Physicists knew how to calculate with waves. They calculated waves as an undergraduate in college. They knew how waves went around and formed orbits. So the appeal of the Schrodinger picture was that it was pictorial. It was almost Newtonian. It was continuous. None of this quantum business. And you could calculate with it.
So which is it? Is matter made up of waves or particles? They seem to be complete opposites. Waves can pass through one another, sometimes canceling each other, sometimes making even bigger waves. But particles, on the other hand, bounce, smash, exert a force when they meet. They can't cancel each other out.
So these two pictures clashed with each other, and they debated, and they had arguments, and they yelled and screamed at each other. In fact, one day Heisenberg was so worried that he simply came down with hives and hay fever and tremendous case of allergies, worrying about whether or not the rival picture was correct.
In 1926, Bohr and Heisenberg invite Schrodinger to Bohr's new institute in Copenhagen to try and work out their differences. Heisenberg writes about the visit.
Though Bohr was an unusually considerate and obliging person, he was able in such a discussion to insist fanatically and with almost terrifying relentlessness on complete clarity in all arguments. He would not give up, even after hours of struggling, until Schrödinger had admitted that his interpretation was insufficient. Every attempt from Schrödinger's side to get around this bitter result was slowly refuted point by point in infinitely laborious discussions.
Bohr's wife nurses Schrödinger when he falls ill from exhaustion. She brings him tea and cake, even as her husband sits on the edge of the bed continuing the argument. Still, Schrödinger clings to his classical view, wearily noting at one point, if one has to go on with these damn quantum jumps, then I'm sorry I ever started to work on atomic theory.
The essence of the Bohr-Heisenberg picture was that the electron was a particle. However, there was a certain amount of uncertainty with regards to where the particle was. Now, one day, Heisenberg was so paralyzed, worrying about all these problems, that he took a walk in the park. Outside his institute, there's a famous park, and late at night, he walked through the park wondering, how can it be? How can it be that you don't quite know where the electron is? And then, in a flash, he understood. Because to understand where an electron is, you have to look at it. To look at it, you have to shine a light on it. But when you shine a light on it, that disturbs where the electron is. So the very fact of observing an object changes its location. Therefore, he realized that uncertainty is an essential part of his picture.
Heisenberg calls his insight the uncertainty principle. In a clear mathematical way, it says, the more you know about a particle's position, the less you can know about its speed and direction. The opposite is also true. The more you know about a particle's speed and direction, the less you can know about where it is at any given time.
And when he finally had that idea, he realized that he could merge the Schrödinger picture with the Bohr-Heisenberg picture to give us the modern-day theory of the quantum principle. In other words, the electron is a point particle, but you don't know quite where it is. And the probability of finding it at any given point is given by a wave, the Schrödinger wave. So we now have this beautiful synthesis of waves and particles.
Heisenberg's principle indeed is very, very non-intuitive. Frankly speaking, I call it bizarre. But you can see it at work.
So what he's about to show you is, I think, proof of Heisenberg's uncertainty principle. But he doesn't use electrons. He uses light. He uses a laser beam. A laser beam is a wave that has quantum properties. Okay. If he can demonstrate Heisenberg's uncertainty principle using a wave, that suggests that electrons aren't pure particles, because waves do the same thing. What he's going to do is pass a laser beam onto a screen, and then he's gonna narrow the width through which that laser beam travels. And what happens after that slit gets really narrow demonstrates Heisenberg's uncertainty. So you'll see, it's just that he's using a wave to do it.
Laser beam because it's bright, but I could use any other light for that matter.
Yeah.
And I make here an opening, a slit, a vertical slit.
Clearly didn't dress up.
And here
Video, right?
goes the laser beam right through the slit. Light goes on, and here I project this onto the wall, screen, projection screen. And what do I see? Well, you see exactly what you predict. You see here this laser spot from this beam. But now I'm going to make this vertical slit narrower and narrower and narrower. What now are you going to see? Well, you're going to see exactly what you predict. You're going to cut off the edges of the circle, and the spot gets narrower and narrower and narrower. But now you come to the point that this narrow slit, say, is only 1/100th of an inch wide. And now Heisenberg's principle comes in, because now you know so precisely in the horizontal direction where the light is, that as it emerges from this slit, the direction of the light is no longer determined according to Heisenberg's principle. And so now what you're going to see, it's going to spread out in the horizontal plane, and therefore what you're going to see on this projection screen is going to get wider. Extremely non-intuitive. Because what am I doing? I'm making the slit narrower and narrower and narrower and narrower. And what do you see ultimately? That the beam horizontally becomes wider and wider and wider and wider and wider and wider and wider. Now that is very non-intuitive, but it's the way the world works.
According to the quantum theory, even the most bizarre events have a probability of taking place. There's a certain probability that I will dissolve and simply rematerialize on the other side of that brick wall. Now, you may say to yourself, well, that's impossible. We've never seen anyone dissolve and rematerialize on the other side of brick walls. But we actually give this problem to our graduate students, to our PhD candidates. We ask them to calculate, using the quantum theory, what is the probability that you will find yourself on the other side of a brick wall? Now, to tell you the truth, you would have to wait longer than the lifetime of the universe for such an event to take place. So you don't have to worry. Your atoms are not going to dissolve, and you're not going to rematerialize on the other side of brick walls, but there is a probability you can calculate for that event happening.
And then you can ask yourself the question, do I understand it? I don't even know what that means, understanding. I have problems with that. Physics describes things, describes phenomena.
I like it better.
And as long as it is predictable, as long as that formalism applied in a certain situation gives you the right answer, who cares? Who cares what the meaning is of understanding? I think I leave that up to philosophers. And I think they don't have a clue either, of course, but there are some physicists who refuse to accept that quantum mechanics represents the full story of the subatomic world. The most famous is Albert Einstein.
Quantum mechanics is very worthy of regard, but an inner voice tells me that this is not the true Jacob. The theory yields a lot, but it hardly brings us any closer to the secret of the old one. In any case, I am convinced that he doesn't throw dice.
He couldn't believe that there were big patches of the world about which we could not know. And his idea from early on in his life, all the way to the end of his life, was that there ought to be a set of equations, deterministic, causal, ordered, formulated in such a way that they could tell us everything about a future in terms of everything about the present. And quantum mechanics wouldn't allow it. He couldn't stand that idea.
The world's greatest physicists gathered in Boston in 1927 Einstein challenges Bohr in the idea that uncertainty rules the world. Werner Heisenberg writes in his diary,
We all stayed at the same hotel. The discussion usually started at breakfast, with Einstein serving us up an imaginary experiment by which he thought he had definitely refuted the uncertainty principle. In the course of the day, we would have discussions on the matter, and as a rule, by supper time, we would have reached the point where Niels Bohr could prove to Einstein that even his latest experiment failed to shake the uncertainty principle. Einstein would look a bit worried, but by next morning he was ready with a new imaginary experiment more complicated than the last.
one of Einstein's challenges is so clever, it has Bohr deeply concerned for the future of quantum mechanics. Physicist Leon Rosenfeld writes,
Bohr did not see the solution. I shall never forget the sight of the two antagonists leaving the hall. Einstein, a tall, majestic figure, walking quietly, with a somewhat ironic smile, and Bohr trotting near him, very excited. During the whole evening, Bohr was extremely unhappy, going from one scientist to another, trying to persuade them that it couldn't be true, that it would be the end of physics if Einstein were right.
Bohr spends a sleepless night in his hotel room before he discovers a flaw in Einstein's argument. Ironically, it involves a subtle application of Einstein's own theory of relativity.
Bohr and Einstein are an astonishing pair. In many ways, they loved each other. They loved talking to each other. They loved engaging with each other's ideas. And yet they wanted such utterly different things from physics that they never really could see eye to eye.
God does not throw dice was Einstein's unshakable principle, one that he would not allow anybody to challenge. To which Bohr could only counter, nor is it our business to prescribe to God how he should run the world. Einstein and Bohr had their last battle about quantum mechanics in 1933.
Also, section 5. What we're going to do in section 5.4 is accept the fact that this is difficult to understand. If you find it difficult to understand, Dr. Levin said, relax. He doesn't understand anything. But the fact is, number one, it's the best we can do, and number two, it works. So what we're going to do in section 5.4 is, okay, that's the theory. Now let's practically apply it. So what we're going to do is we're going to go through an atom at a time. And we're going to describe for each atom where the most likely locations of those atoms' electrons are. We're effectively going to use Schrodinger's equation to say, okay, we'll start with hydrogen, the simplest atom. And we'll take hydrogen's electron and we'll say, okay, in the first energy level, where's the most likely location in three-dimensional space for an electron with that size nucleus to be spending most of its time? Then we're going to take that electron and we're going to give it n equals 2 energy. And every time we give it more energy, there's more probability volumes that we see. Then we're going to give it n equals 3 and n equals 4. And that's just hydrogen. As soon as we go to helium, we'll realize that electrons affect each other. So things get more complicated. And then you'll read about quantum numbers, the principal quantum number, the angular momentum quantum number, or second quantum number, the third quantum number, or magnetic quantum number, and the fourth quantum number. And by the end of section 5.4, I could give you any atom in the periodic table. Right, the electron configuration. And you'll be able to say that's easy. Xenon, 4F14, 5D10, 6s1. Nothing to it. You'll also be able to draw out vertical diagram, vertical energy diagram of the orbitals that electrons are most likely going to occupy, probability modes. Notice in the back of the book, this periodic table, we separate the periodic table from each office. There's a reason we did that. That's as prescribed by quantum mechanics. You're going to learn what those 4 blocks represent. You're also going to see that that periodic table is effectively in that form before the details of quantum mechanics were worked out. All quantum mechanics did was confirm that that's the way the periodic table should be. We put that together, not based on any quantum mechanical theory. We put it together based on behavior. But when quantum mechanics was applied to the periodic table, there was a 1-to-1 correlation. The reason the periodic table looks like that, the reason elements are where they are, is based on quantum mechanics. And there are few examples in science, if there are any, that are that good a marriage between experiment and theory. The theory, all it did is confirm everything that years and years and years of experimentation had given us in terms of how the elements are related to each other. And remember, the laws don't say why, they just say what. So Mendelev's periodic law, if elements are arranged in order of increasing, originally we said mass, but the modern version is if elements are arranged in order of increasing atomic number, pattern can be seen with similar properties recurring related to the periodic basis. But he had no idea quantum mechanics applies to that. And we're going to spend almost an entire chapter on that. But what we're going to do in section 5.4 is apply quantum mechanics to electrons and atoms, which is the title on page 268. So what I'd like you to do for Thursday, without bending your mind too much, see if you can read to page 271. Try the quick check on the bottom of 271 if you want. You're going to learn about the first, second, and third quantum number. You're going to see what an orbital diagram looks like. But that's good for having. And then we're going to go to multi-electron. And then we're going to learn about a fourth quantum number called a spin quantum number. And remember, even if this doesn't make any sense to you, even if something being apart on a way to something you can't let your head around, relax. You're in good company. The fact is, it still works. And I'm not going to ask you on a test, do you understand it? I don't. It's just the way the world works. I like the guy from MIT. Didn't do to put on a 3-piece suit to get interviewed. And as I said, I don't think he knows that MIT has a dental plan. But he was just excited about what he was learning. And to admit, people ask me if I understand. I don't know what the meaning of that word understanding is. That's pretty cool. If the guy that is at the top of his game worldwide, physicist at MIT, admits that, then perhaps other people pretending that they understand it completely are just blowing smoke. So I tend to gravitate towards the guys that are a little more humble. Einstein kind of was. God doesn't throw dice. Well, maybe he does. Maybe he does. Anyway, that's discussion for another time. I've had a number of questions from people saying, well, I'm going to go on holidays early. What am I going to miss? Section 5.4 is gonna take us a while. Because we're gonna be going through Adams at least probably up to the end of the period done at a time. Right? So at least until Christmas. And that's gonna take a while, and that's gonna take diagrams. So I see you guys once more this week. And we haven't started section 5.4 yet. Then we have 3 times next week. So is the test gonna be before spring break? No, it will not. It will not. More than likely, what I'll do is I'll get close to finishing section 5.4. Probably the idea will be upon return from spring break, we'll have a review class, then we'll have a test. You're not gonna get back first thing and write a test. That would mean that my reputation as being a hard ass is actually justified. I don't think it is. I wouldn't do that to you. It would bug me if I was a student and teacher said, they're breaking that, that's just a. How can you enjoy spring break if when you first get back to the test? So I wouldn't do that. But there might be a review. Okay. The plan after that would be after the test and do chapter 6. After 6, we're not gonna do 7, we're gonna do 8, which is organic chemistry. It may look like we've got lots of time left because it's only really the beginning of March, but we don't really. You guys are going on the retreat at some point, correct? That's after spring break. Almost immediately after spring break, we have Easter break. And then you guys go on the retreat, I think. That's not even including all of the band festivities or choir festivities that are always taking students out of class. There's track meets. There's walkathon, house games, youth Olympics, all that imperative stuff. So the remainder of the year, there's not as many classes as you might think. Case in point, not only Thursday do you go to confessions, but Thursday is also a late start for yet another staff meeting. I don't know why. I don't know what we have yet to talk about. Because we haven't talked about much even in the last 3 weekends. So apparently there's another staff meeting. All of that stuff takes time away. And 10 minutes here or there, that's significant. So I'll do the best I can. Sometimes it's not easy. So if there's